Hi guys, in the next series of videos we're going to take a look at what are titrations, looking at the titration process, an introduction to standard solutions, looking at how we make standard solutions, titration calculations, an exam style question, and finally a summary.
So let's have a look at what titrations are. Well, titrations are a form of volumetric analysis, where a known volume and concentration of a solution is reacted with a measured volume of a solution. The results of the titration can be analysed and can be used to find chemical unknowns. These unknowns can include concentration, molar mass, formula, and water crystallization. So before we have a look at the titration process, let's have a look at what we use. We use something called a standard solution. This is a solution with a known concentration and is used in our titrations. We'll take a closer look at the method used in making a standard solution in a later part of this video. Let's first of all take a brief look at the titration process. The first step is to use a pipette to add a measured volume of your first substance X to a conical flask. We then add a suitable indicator to the flask. This indicator depends on the chemicals you're using. We then fill the burette with the other solution, Y. We then open the valve on our burette to allow a small quantity of Y to flow into our flask of X. You can see here that we're turning that valve to allow Y to flow out and into our conical flask of X. We repeat this process until the end point is reached, and we can then measure the volume of Y that has been added. We can then calculate the unknowns by analysing the result of our titration. So what are standard solutions? Well, standard solutions, as we mentioned in the previous part of this video, are solutions of a known concentration. They're used in titrations, which allow us to calculate chemical unknowns. So first of all, let's quickly recap the concept of concentration and that of solvents and solutes. The solute is dissolved within our solvent, and the concentration is a measure of how much solute is dissolved in a given volume of the solvent. So now we've recapped the idea of concentration, let's take a look at the steps involved in making a standard solution. The first step is to carefully weigh out the required mass of our solute. The second step is to dissolve the solute in our chosen solvent in a beaker. The third step is to transfer the solution that we've made into a volumetric flask. We then rinse the beaker with our initial solvent, that's the solvent that we've chosen, and we add the washings into the volumetric flask, making sure nothing is washed away or poured down a sink and wasted. In the fourth step, we add some of our solvent to the volumetric flask, making sure not to fill up to the graduation line. That's a line that you'll see on the neck of a volumetric flask. The fifth step is to add the solvent drop by drop until the bottom of the meniscus is sitting on that graduation line, ensuring we have just the right volume of solution. It's important to not allow the solution to fill above the line. If you do, you'll have to start the process all over again. The final step is step 6, to mix the solution thoroughly, and this is done by inverting your flask multiple times, making sure you put the stopper in tightly first of all. So we've had a look at the method of making a standard solution. Let's have a look at the calculations we do before we start making our standard solution. The first step is to work out the number of moles required. That's the number of moles of our solute required. We then calculate the molar mass of the required substance, and we can calculate the mass of the substance that is required. That's the mass we're going to weigh out. So let's have a look at a worked example so you can really understand these initial calculations. We want to make a 250 centimetre cubed solution of sodium hydroxide with a concentration of 0.1 mole per decimetre cubed. So the first step is to work out the number of moles required. So using our equation pyramid, the number of moles is equal to the concentration multiplied by the volume. We want to know the number of moles. So that's the concentration multiplied by the volume is the arrangement we're going to use. The information we're given was that the concentration required is 0.1 moles per decimetre cubed, and the volume was 250 centimetres cubed. That's equal to 0.25 decimeters cubed. So that will be the number of moles is equal to 0.1 multiplied by 0.25, giving us 0.025 moles required. Now to calculate the molar mass. We're producing a solution of sodium hydroxide, so the molar mass of sodium hydroxide is what we're going to have to calculate. If we look at our periodic table, we can see sodium has a molar mass of 22.99, which we can round to 23. Hydrogen 1 and oxygen 15.99, which we round to 16. So that will be 23 plus 16 plus 1, a molar mass of 40. In our final step, we're calculating the mass required. We know the number of moles is equal to 0.025 moles, and we know the molar mass is equal to 40. So we can look at our equation that the number of moles is equal to the mass divided by the molar mass. The equation rearrangement we're going to use is that the mass is equal to the number of moles multiplied by the molar mass. So that's 0.025 multiplied by 40, giving us a mass of 1 gram that's required. So let's have a look at titration analysis and the calculations that we can carry out. In general, these calculations can follow certain steps, and I'll show you how our calculations can be broken down in these easy to follow steps. Calculations can be used to find unknowns. These unknowns could be the concentration of the solution, the molar mass, and many other things. Exam questions will usually guide you through. It will give you small steps to follow, so don't be worried if a big titration calculation comes up. Let's have a look at some of the calculations that we can do. The first calculation we're going to look at is the calculation of an unknown concentration. 25 centimeters cubed of a 0.1 mole per decimeter cubed solution of a base, sodium hydroxide, is titrated with 22.5 centimeters cubed of an acid, hydrochloric acid. What is the concentration of the acid involved in this titration? So we're looking to find out the concentration of the acid. That's our unknown. So let's answer this question looking at the steps involved. The first step is the reaction equation. We know that our acid, hydrochloric acid, is reacting with our base, sodium hydroxide. And we know that acids and bases react together to form a salt, in this case sodium chloride, and water. Now we can check to see our equation is balanced, and it indeed is. The second step is to calculate the amount in moles of base that has reacted. So what do we know? We know the volume of base was 25.0 centimeters cubed. That's equal to 0.025 decimeters cubed. We know the concentration of our base was 0.1 moles per decimeter cubed. Now, using our equation pyramid, the number of moles is equal to the concentration multiplied by the volume. The number of moles is equal to 0.1 multiplied by 0.025 to give us 0.0025 moles of base. Now to calculate the amount in mole of acid that was used. Looking at the reaction equation up here, we can see that 1 mole of hydrochloric acid reacts with 1 mole of sodium hydroxide. It's a 1-to-1 ratio. So 1 to 1 means that 0.0025 moles of our base will react with 0.0025 moles of our acid, meaning that the number of moles was 0.0025 moles. So now to calculate the concentration. Again, write down what we know. We know the number of moles is equal to 0.0025. We know that the volume of our acid used was 22.5 centimeters cubed. That was given to us in the question. That is equal to 0.0225 decimeters cubed. Now if we look at our equation pyramid, the number of moles is equal to the concentration times by the volume. The rearrangement of this equation we're going to use is that the concentration is equal to the number of moles divided by the volume. So that is 0.0025 divided by 0.0225 to give us a concentration of 0.111 moles per decimeter cubed. So now we've had a look at finding an unknown concentration, let's have a look at a slightly different calculation to find an unknown molar mass. 1.5 grams of an acid was dissolved in water in order to make a solution with a volume of 250 centimetres cubed. 25 centimetres cubed of the solution of this acid, HX, was titrated with 22.5 centimetres cubed of a base, sodium hydroxide, which had the concentration of 0.1 moles per decimetre cubed. What is the molar mass of the acid involved in this titration? So the first step again is to write out our reaction equation. We have our acid HX. Now don't worry that this acid HX containing X as a general element isn't specific, it's just used to represent an acid here. It's reacting with a base, sodium hydroxide. We know acid plus base equals salt plus water. The salt is going to be NaX and we're going to form a water. Checking to see our reaction is balanced, which it indeed is. We can then move on to step 2, which is quite similar to the step 2 of our previous calculation. We're going to calculate the amount in moles of base that has reacted. So let's write down what we know. We know the concentration is equal to 0.1 moles per decimetre cubed, as we're given that in the question. And we know the volume of our base that was used was 22.5 centimetres cubed. That is equal to 0.0225 decimetres cubed. So we can write out our reaction pyramid that the number of moles is equal to the concentration multiplied by the volume. To see that the rearrangement we need to use is the number of moles is equal to the concentration multiplied by the volume. The concentration is 0.1 moles per decimetre cubed and the volume is 0.0225, giving us 0.00225 moles of base that has been used. So now for the third step, to calculate the amount in mole of acid that was used to make the initial solution. So if we have a look at our reaction equation, we can see that 1 mole of HX reacts with 1 mole of sodium hydroxide. So that's a 1-to-1 ratio. That means that 0.0225 moles of our sodium hydroxide will react with 0.00225 moles of our acid HX. Now, importantly, this is telling us that there is 0.0025 moles of HX in the 25 centimetre cubed sample. We want to know how much there was in the initial 250 centimetre cubed solution. Now we know that 250 divided by 25 is equal to 10. So looking at the volume, that's 10 times as much, meaning there's going to be 10 times as many moles. So that's 0.00225 times 10, giving us 0.0225 moles of acid in the 250 centimetre cubed initial solution. Now the final step, to calculate the molar mass of the acid that we used. Well, we know the number of moles is 0.0225, we've just calculated that, and we know the mass of our acid was 1.5 grams, we were given that in the question. So using our reaction pyramid, that the number of moles is equal to the mass over the molar mass, we can work out that the molar mass will be the mass divided by the number of moles, that's 1.5 divided by 0.0225. to give us a molar mass of 66.667 grams per mole. A student decides to make up a standard solution of sodium hydroxide. She carefully measures out 10 grams directly onto a balance. She adds this to a conical flask with 100 ml of water and stirs using a glass rod. Part A. The student made a number of errors in her method. How could she improve her method? So for 3 marks, we should probably give about 3 errors if we can find them. So let's take a look at her method. It says here that the student measures out 10 grams of sodium hydroxide directly onto a balance. It's probably better for the student to use a weighing boat to ensure that no residue is left behind, as the weighing boat can easily be washed out to ensure that all of our chemical reactant is being used. So the first improvement is she could use a weighing boat. In the method, we're then told that she adds this to a conical flask. The student could instead use a volumetric flask to ensure that an accurate solvent volume is measured. And for our third and final suggestion of improvement, the method says that the student stirred using a glass rod. Alternatively, the student could invert her flask, in this case her volumetric flask, which we said she should use, to ensure that no residue is left on the glass rod. So for each of those corrections, we receive 1 mark. She could use a weighing plate, she could use a volumetric flask, and she can invert the flask rather than stirring with her glass rod. Moving on to part B. Having learnt the correct way of making up a standard solution, the student decides to make up a standard solution of MgOH2, magnesium hydroxide. The student wants to obtain 1 litre of 0.1 moles per decimeter cubed solution. What mass of magnesium hydroxide should she use? Let's first of all draw out the pyramid that we're going to need. We know that the number of moles is equal to the concentration multiplied by the volume, so we can go ahead and calculate the number of moles of magnesium hydroxide in the solution. So we know the concentration is 0.1 moles per decimeter cubed, and we know the volume is 1 litre, so that's 1 decimeter. So that gives us 0.1 moles. So now we can go ahead and use our second pyramid. Number of moles is equal to the mass divided by the molar mass. We know the number of moles is equal to 0.1. We want to know the mass, and we can calculate the molar mass. If we take a look at our periodic table, we can see that we can find all the components we need. We want to find out the molar mass of magnesium hydroxide, MgOH2. We can see that we have hydrogen over here with a mass of 1, oxygen over here with a mass of 16, and magnesium over here with a mass of 24.3. So the molar mass will be 24.3 plus 16 times 2, as we have 2 oxygens, plus 1 times 2 for our 2 hydrogen atoms, to give us a total of 58.3. That is our molar mass of magnesium hydroxide. So putting that into our equation, we can see that the mass is equal to the number of moles, 0.1, multiplied by 58.3, our molar mass, to give us 5.83 grams that we require. So the answer is 5.83 grams of magnesium hydroxide. So this question holds 2 marks. The first comes from correctly calculating the number of moles of magnesium hydroxide in our solution, and the second from a correct final answer of the mass of magnesium hydroxide we need. So let's go ahead and have a look at question 2. A titration between sulfuric acid and sodium hydroxide is carried out. The equation for the reaction is shown below. We're given the equation here. 25 centimeters cubed of 0.040 moles per decimeter cubed of sodium hydroxide is neutralized by 17.5 centimeters cubed dilute sulfuric acid. Part A asks us to calculate the amount in moles of sodium hydroxide used in titration. Now, this is very similar to the second step of the equations that we were doing before. So write down what we know. We know that the concentration is equal to 0.0440 moles per decimeter cubed, and we know the volume is 25.0 centimeters cubed, which is 0.025 decimeters cubed. We can look at our triangle pyramid, which is the number of moles is equal to the concentration multiplied by the volume. So N is equal to C times V, which is 0.0440 multiplied by 0.025 to give us 0.0011 moles of sodium hydroxide used. So now let's look at part B. Calculate the amount in moles of H2SO4 sulfuric acid used in the titration. So in order to do this, we need to look at our reaction equation. Now we can see that 2 moles of sodium hydroxide will react with 1 mole of sulfuric acid. So that's a 2-to-1 ratio. So if we have 0.0011 moles of our sodium hydroxide, it's going to react with half as much sulfuric acid. So that's 0.0011 divided by 2 to give us 0.00055 moles of sulfuric acid. Part C, our final part, is to calculate the concentration in moles per decimeter cubed of H2SO4 sulfuric acid used in titration. Again, as we always do, write down what we know. We know the number of moles is equal to 0.00055 moles, as we've just worked out. And in the question, we're told the volume is 17.5 centimeters cubed. That's equal to 0.0175 decimeters cubed. So our equation pyramid shows us that the number of moles is equal to the concentration multiplied by the volume. We want to know the concentration, so the rearrangement that we'll use is that the concentration is equal to the number of moles divided by the volume. So that is 0.00055 divided by 0.0175 to give us a concentration of 0.03143 moles per decimeter cubed.
Question 3. A student carries out the titration using barium hydroxide and nitric acid. In part A, we're asked to write an equation for the reaction taking place. So we know our two reactants are barium hydroxide and nitric acid. Now we're going to form salt and water, our salt being barium nitrate. So now I've written our equation, we need to go ahead and check to balance it. So on both sides of the equation we have 1 barium. On the left hand side we have 1 nitrogen. On the right hand side in our product we have 2. So we can balance that by putting a 2 in front of our nitric acid. To check our hydrogen atoms, we have 2 here and 2 here. That's 4 on the reactant side, the left hand side. And we have only 2 on this side. So we'll put a 2 in front of our water molecule. So now we have 4 on both sides. To check our oxygen atoms, there's 2 here and 6 here, that's 8. And we have 6 here and 2 here, 8 again. So that is our correct and balanced equation. And for that we get 1 mark. In part B, we're told that 50 ml of barium hydroxide, a concentration of 0.5 moles per decimeter cubed, are required to fully titrate a 100 ml solution of our acid. We're asked what is the initial concentration of the acid. So the first thing we're going to do is write out the pyramid we're going to need. We know that the number of moles is equal to the concentration in times the volume of our solution. So we're going to work out the number of moles of barium hydroxide that have been used in the titration. So the number of moles is equal to the concentration multiplied by the volume. The concentration is 0.5 moles per decimeter cubed, and we have 50 mils. So we're going to multiply that by 50 over 1000, converting the mils there to decimeters cubed, giving us 0.025 moles. Now, if we take a look at the equation that we previously wrote, we can see that 1 mole of barium hydroxide reacts with 2 of nitric acid. So that's 1 to 2. Therefore, if we have 0.025 moles of our barium hydroxide, that's going to react with 0.05 moles of our nitric acid. So we know we have 0.05 moles of nitric acid that's reacting initially. We know there's 100 mils of the solution, so let's go ahead and quickly note down what we know. We know the number of moles is 0.05. We know the volume is 100 mils, so that's 100 over 1000, converting to decimeters cubed, giving us 0.1 decimeters cubed. Now, using the same pyramid, we can calculate the concentration, seeing that the concentration is the number of moles divided by the volume. So that's 0.05 divided by 0.1 to give us 0.5 moles per decimeter cubed. So, this question holds 3 marks. The first mark is given for correctly calculating the number of moles of barium hydroxide. The second for applying that and using that to calculate the number of moles of acid. The third and final mark for correctly calculating the initial concentration of the acid, remembering to give units. Part C, the last part of our question, asks us to name 2 pieces of apparatus that are used to accurately measure the volume of solutions in a titration. And we're asked what other chemical substance must be added to the reaction flask for a titration to be successful. So if we deal with the first part of the question, to name 2 pieces of apparatus that are used to accurately measure the volume of solution in a titration. This could be a burette and also a pipette.
which are two important pieces of apparatus that you will have used that are used to accurately measure volumes of solution, often small volumes. Now to deal with the second part of the question. What chemical substance must be added? Well, we know that it's important to use an indicator because this will tell us when we have reached the end point of our titration, or when we are near it. There are a variety of different chemical indicators that have been used. We're not asked to give a suggestion of one here, just to explain what chemical substance would be added. But some questions may ask you to go into more detail and suggest an indicator, such as methyl orange or phenolphthalein. This question holds 3 marks. You get 1 mark for each suggestion of a correct piece of apparatus, and the third and final mark comes from stating it's an indicator that needs to be added.
Hey guys, I hope you're enjoying the video. If you're looking for an amazing A-level chemistry resource, join me today in my series of engaging bite-sized video tutorials. Just click the SnapRevise smiley face and together let's make A-level chemistry a walk in the park.